So now we're going to move on to Kelly Garner, who's a postdoctoral Marie Curie research fellow working with far too many institutions and people for me to list. So Kelly, I'm just going to have you take it away.
Sure, thank you. Just give me a moment and I will share my screen. Okay. One moment. I should be able to share just the presentation slides with you, right? Just the browser. I feel Zoom is not behaving. Here we go. This is what I want to do. Okay, so you guys can all see that, correct?
Yeah, looks great.
Beautiful. Okay. So this is the human basal ganglia. This collection of nuclei have been strongly implicated in the influence of associative learning on action selection. So we're interested in mapping the functional changes in the basal ganglia when associative learning instead influences visual selection, as this is currently largely underspecified. However, these regions are tough to image. Their higher iron content relative to the cortex means that signals detectable by MRI decay sooner than other regions. Therefore, to accurately map functional changes during visual selection, we need to identify the best protocol to image the basal ganglia. So that's our aim, which is to compare 70 MRI protocols for signal quality when participants complete a task that taps the influence of learned associations on visual selection. So how we did this, we recruited 5 participants who completed 4 sessions. The first was a task learning session where they performed a variant of the Posner queuing task. Participants responded whether a Gabor was oriented clockwise or counterclockwise. The target and distractor were preceded by probabilistic, spatial, and reward cues, and I can go into those during questions if desired. So then participants performed this task over 3 sessions in the 70 MRI scanner, where we compared 3 imaging protocols counterbalanced across sessions. The details of the protocols are listed here, and the protocols were each optimized for different spatial and temporal resolutions. So for now, just note that they differ in their TR, and I shall refer to them by their TRs from now on. So then we assessed the signal quality by using the contrast noise ratio. So the way we calculate this is we fit a GLM to our data and we ask what is the ratio between our estimate of the amplitude of a contrast of interest. So this could be the response hand that participants are using. And what is the ratio of that estimate to the standard deviation of the residuals of the model. Thus, we have a measure of the size of our effect of interest relative to a measure of the noise in our data. Okay, so this is example CNR data from 1 participant over our 3 sequences. The brain is intersected so you can see across a few of the ROIs. Because for my question, I care about the magnitude rather than the direction of the difference, I'm going to extract the voxels from each ROI and compute the average root mean squared CNR for that region. And that's what I'll take you through now. So just to recap, on the left, we have our regions of interest, which comprise the subnuclei of the basal ganglia and a few cortical nodes we identified using a neuroscience meta-analysis. And here we're looking at the RMS CNR measure for the response hand contrast. So remember, we know that the basal ganglia is well implicated in action selection, and this is a typical contrast to use when assessing signal quality in the basal ganglia. So here we have our CNR measure plotted by the TR on the x-axis, or the protocol on the x-axis, with each subject plotted as a single line. And this is for the global pallidus external region. And so now I show you for all our ROIs. And as you can hopefully see, we don't see any particular pattern in the cortex, which is that top row of plots there. But we do see a statistically significant trend in the basal ganglia ROIs. for the protocol with the shortest TR offering the best signal. So now the question is, do we get a similar result when we look at a contrast that is not typically used to assess signal quality in the basal ganglia, such as on which side the target was presented? And that's what I'm showing you on the left here. So again, we see a non-consistent pattern for our cortical ROI. But hopefully you can see we actually see the opposite pattern in the basal ganglia, where now the protocol with the longest TR offers the best signal. Therefore, it appears that if you're optimizing your protocol, this can be dependent on the contrast that you're using and the regions that you want to look at. So in conclusion, when mapping the functional activity of the basal ganglia, the optimal protocol appears to differ dependent upon what you seek to map. Protocols that are good for mapping motor activity are not the same as those which are best for mapping shifts in visual spatial attention. And we need to disentangle whether this is due to the changed temporal or spatial resolutions, or if there's an interaction between the timing of mental events and the hemodynamic response function. And so I'd just like to say thanks to my collaborators and for your attention.
Awesome. Thank you so much, Kelly. So please feel free to put your questions in for Kelly or for our previous two speakers. I will abuse my position as MC and take the first question. So what, I know you mentioned sort of some next steps, like what's your sort of future directions on this project, Kelly?
So our future directions are to now run a larger study using our best protocol, so we can start teasing apart how learning about probabilities and reward values influence visual selection. So the story of what we know about visual selection so far is very cortical based, and we're a bit underspecified, but we know the basal ganglia should be contributing to learned association, so that's really what we're looking to pin out next.
Awesome, very cool.
I have a question for